Can you guys hear me? All right, we've got a few minutes here before we start up, and I know sometimes there are questions. If you guys that are here, if you have any questions, you're welcome to start. There was a question in the chat. What week are we going to have our exams? Yeah, I need to settle this. I need to see how far we are with the material. So it's I mean, in general, what's going to happen is that we have to get through all the material that we need, and then we'll have the exam. And the way I like to do it is to have some time before the exam where we can have some discussion about the various exam questions. So typically it comes towards the end of October. I'll try to have a look at the schedule and try to make a better estimate of when it's going to be. So towards the end of October, and then I'll get back with more precise information sometime later this week. And yeah, so when you look at the schedule on Canvas, the way that let me just show you. We go into Zoom and then down to wherever we can find the schedule. Right, so it's here. So you go all the way down to the end, and so this is what we need to get through. We need to get through all this material here, and currently what we're looking at is we are in here conditional expectations. So retinicodem, this is coming today, and then we're going to talk about existence and examples. So we are right around here. We need these two blocks here to be covered too, and then here there should be at least one time where we will have questions and answer session, and then we'll start scheduling the oral exams. Yep. Other questions or comments? So we have the oral exam next week. No, as I just said, we will have it towards the end of October. We have to get through the next couple of weeks of material. Then after that, there should be at least one lecture where we can have a discussion, question and answer session, and then the exam is going to come. So it'll be towards the end of October. Yeah, are there other questions? Okay, if that's not the case, then I say we get started. So what we're going to be doing today is, so again, we are working in the thicker, the second stochastic calculus for finance book. And what we're working on is over here in chapter 2. We've been talking quite a bit about expectations and these stochastic integrals. Last time we talked about how to relate these Lebesgue integrals to the usual Riemann integral that you see in calculus. So what's going to come today is we're going to be looking at this change of measure section 1.6, and then ultimately what we want to do is get down here in section 2.3, which is this conditional expectations. So this is, you can see this is a big chapter. This is like 10 pages, general conditional expectations. And so the way that it goes is, so our goal is, the next goal is to define the conditional expectation. Is to define this where x is a random variable and g up here, this is a sigma algebra which is inside F. That's our next, this is our next big goal. Right, we already have, so we have defined and discussed the expectation of this guy when x is integrable. So we have defined the, so there are many ways to write this. You can also write this here as an integral over omega of x and dp. We have discussed and defined this is this Lebesgue integral. What comes next is moving from these expectations here to the ones that you have up here. And you've probably seen stuff like an expectation of, say, x, and then given, say, y is y, or and maybe you've seen probabilities like expectation of x given a set B. Right here you can use, you've probably seen expressions like this, or maybe you have seen something like P of A given B. You've probably seen expressions of this form in your probability class at some point. And now we're going to be using this thing up here. This is what we want to get to. And of course, what has to happen is that this new notation up here is going to be more general than the ones we have down here. So we need to make sure that whatever the definition of this object that we're trying to get at, whatever the definition of this will be, it must be consistent. It has to be consistent with what you're seeing before, right? So that's a must. And this is just like when I compute the expectation of x, I can write this here as an integral of f. I can integrate out if there's a density. Just like this more general integral we had to be consistent with what you've seen in calculus when x has a density. So the more general notion of a conditional expectation, the one that we're trying to get at, this one, it has to have the property that you get the formulas back that you've seen in earlier classes whenever those assumptions are met that you've stated these formulas under in those earlier classes. Okay, so the question is, what is the general definition of this conditional expectation? Okay, so before we do that, we're going to go on a big detour. So the prep work for defining this object here, the prep work for this thing goes through quite a detour. We're going to be talking about change of measure. Right, so remember, in the binomial model, we had probabilities P, and we had a probability measure P tilde. And change of measure is formalized through, so the big result in that literature, in that theory, is called Radon-Nikodym's theorem. So this is Radon-Nikodym's theorem, and what's called Radon-Nikodym derivatives. So this is something that I'm not assuming you guys have seen before. And there's the word derivatives. So it's a bit unfortunate that it's called a derivative, because it's not a derivative from calculus. This is not a calculus derivative. Calculus derivative. And it is not, it's not an option either. So this is the third kind of derivative that we're going to be discussing in this class, but this is what it's called, a Radon-Nikodym derivative. Okay, so it has to do with changes of measures. So in the binomial model, the one we had, we started out with some probabilities P, and we very quickly switched over to these P tilde probabilities. And so the general structure is what is underneath. What is the general structure underneath that, and what does Radon-Nikodym's theorem say? Okay. So I know traditionally this material here, this has caused headaches in the past. I can say that radionuclidim derivatives, this is something that plays a major role in quantitative finance. The changes of measure, this is everywhere to be found. Just to give you an idea about it, you can look at our textbook and see, just glance through it and see where do you see something that has to do with changes of measures. Right? It comes here in section 1.6, but there's a lot more of it. If you go over and see, there is something here called risk neutral measures. So this entire chapter here is about changes of measure. And the fancy word with radionuclidim when it comes to continuous time finance is this word. You'll see, and we will talk a lot about that when we get there. It's this word Gisanow's theorem. Where do I see it? Gisanow's theorem. So the entire section, entire chapter 5 here is about changing measure. If we look over in our binomial model, if we switch over and have a look in the thinner one, the picture is similar. You're going to find changes of measure quite a bit in here. If you move down, you can see here changes of measure and radionuclidim derivative. So changes of measure, this is really very, very important tool when it comes to quantitative finance. And as I said, the main result we need from measure integration theory is radionuclidim's theorem that we're going to be talking about now. Okay, so we're going to take it slowly, and we're going to start by talking about how to classify measures. So what we're going to do is we're going to have two measures, P and Q. So P and Q, the probabilities on this omega and F. Right, so we have two probabilities on there. So we say that P is, and here comes the first new word, absolutely continuous with respect to Q if what? If Q on a set A is 0, if that implies that P of that set is also 0. So we say that P is absolutely continuous if this implication is true. In which case we write this P and then these two less than or equal to signs. So instead of writing that implication up here, instead of writing P is absolutely continuous with respect to Q, what people write is this P and then these two less than or equal to. And of course, we can swap the roles of P and Q. And if we swap the roles of P and Q, so we'll say that Q is absolutely continuous with respect to P if we swap the roles of P and Q. So we're going to get that if P of a set is 0, if that implies that Q of that same set is also 0. In which case we write, swap them again here, we write Q is absolutely continuous with respect to P. Okay, so we have two probabilities. We talk about how they're related, that means what we have here is that if a set has mass 0 under the measure Q, well, then it's going to have mass 0 under P as well. If that happens, you're going to say that P is absolutely continuous with respect to Q, and then you swap the roles of P and Q, and you get the analog down here for Q being absolutely continuous with respect to P. The third property is, the third definition is that if both P is absolutely continuous with respect to Q and Q is absolutely continuous with respect to P, if both of these hold, we say P and Q are equivalent. And we write this P and then a tilde and then Q.
Does equivalent mean like they're the same measure, or like is an equivalence class that kind of equivalent?
No. It means that if you have two measures that are equivalent, then if you have something that has probability 0 under one, it's going to have probability 0 under the other one. And this is if and only, right? So something has, a set has no probability under, has 0 probability under one measure, if and only if it has 0 probability under the other measure. Okay, so let's do an example. Let's do an example. And I'm fishing out an old exam question. It's one of the ones that's on that set of problems that form the basis of the oral exam. And so I'm looking here at problem number 16. I printed it out way too small, so I'm going to restate the problem with a pen here. But we're looking at problem number 16 in this set of oral exam questions. So let's do an exercise. So this is number 16. So we have a random variable. We have a random variable x. It's going from omega into r. We're going to assume that if I compute the probability that x is less than x under the measure p, the way that that's going to happen is I'm going to integrate out in the normal density. So I'll get, so we're going to assume that we have a measure p such that this is the case. And we're going to assume that we have another measure q such that when I look at x less than x, I get something else. And the thing I'm going to get is a bracket. So it's going to be 0 when x is less than 0. And it's going to be an integral from 0 to infinity. No, 0 to x, sorry, we're integrating up to x. 0 to x of e to the minus y dy. This is what happens when x is positive. So what I have here is the normal. And what I have here is the exponential. So if I have such two measures, p and q, under which this is true, we can ask, what kind of properties do I have? Are they equivalent? Are the what are they? So for example, this is the second question. So do we have the implication? Do we have the implication that Q of A is 0, does that imply that P of A is 0? That was one of the ones we had over here. That was the one, that was this one. Do we have that? If the measure Q is 0, then you also get P. If that's the case, then you say P is absolutely continuous with respect to Q. So we're asking, do we have this property? Any guesses? So under one measure, I'm normal. Under another measure, I'm exponential. Does it seem like these two, does it seem like I have some sort of an implication? So Alice says no. I agree. So no, we need to give a counterexample. Alice, do you have a good suggestion for what A should be? Zero. So let's look at the set X is less than 0. What do we get? Then Q, what is the probability that X is less than 0? That should be 0, right? And what do we get if I plug the same set into P? What do I get if I plug the same set into P? The normal, you're going to get a half. Right, so we do not have that property. So P is not absolutely continuous with respect to Q. So what about the other way? Do we have the implication? Do we have the implication that if P of A is equal to 0, then Q on that set is also equal to 0? So if there's a set, P doesn't see the set. P doesn't see the set, so then what? Do we know that Q also doesn't see the set?
Is the normal distribution ever 0?
Yeah, we had a discussion last time that if I take A to be the set where X is equal to 0 or X is equal to...
Right, if you take like 1 point. Okay.
Oh, but be careful. We had discussions about that last time too, right? These null sets, they can be much more complicated than just a few points, right? We had a discussion about the Cantor set, and the Cantor set is uncountable, right?
Yeah.
So just because you have 0 probability, it doesn't mean that the set is just a few points. It can be quite complicated. So be careful about it. So this doesn't mean that A just has a few points in it. It can have like uncountable many points in it. But what do we think? If P doesn't see it, does Q see it? And so the answer here is yes. Okay, so one way to argue here, so one way to show this goes through constructing a radon Nicodim derivative. Okay, so let me talk about what that is. And then we're going to come back to this example here. And then, so we'll be back in just a little bit after we talk a little bit about radon-Nicodom's theorem. So what is a radon-Nicodim derivative? So one way to show this goes through constructing a radon-Nicodim derivative. So a random variable this is very often denoted by, this is often denoted by dq to p or z. So a random variable, one of these two. So here, this is one quantity, this ratio, dq to p. It's not like there are two things taking a ratio here. This is just one quantity. This is just like C is one quantity. So a random variable, I'll note about this. So let me call it, so let's settle on this one. This is called a radon-Nicodim derivative if so there are a couple of conditions that has to be whole. So one is it has to be positive. It has to have expectation 1. So I'm going to compute the expectation. The man is 1. And 3, when I compute the probability of a set A under this measure Q, this is called the radon-Nicodim derivative. So this is Q's derivative with respect to P. Right, so this is Q's radon-Nicodim derivative with respect to the measure P. If I can compute the probability by performing an integral over A of this random variable dq dp, dp. Right, so we can also write this as an expectation of 1A times dq dp. If I can do this for any A in my sigma algebra, so if the sigma algebra is denoted by F, which is for any set A. So I take a random variable, it's you can see it from the formula, right? That this random variable, it has to be positive because Q of A is positive. So if I start integrating something here that's negative, I'm going to have a negative value for my Q. You can also see from the second point that if I take A here to be omega, if I take A to be omega, I'll get Q of omega. Well, Q is a probability measure, right? So we want Q of omega to be 1. You go over here and you're going to get exactly that. That's the expectation of dq to p. Okay, so that's why that second condition is there. So this is radon-Nicodim derivative. If I have this nice formula, then I can compute the probability under the measure Q simply by integrating this radon-Nicodim derivative over that set that I'm interested in computing the probability of. And so the theorem of radon-Nicodim. So this is radon-Nicodim. Radon-Nicolem's theorem, it says that Q is absolutely continuous with respect to P if and only if there exists a Radon-Nicolem derivative. DQ. So two meshes, you have this absolute continuity property, even only if they're linked through, this formula here. So if you go back to the problem, we've been asked, do we have absolute continuity of Q with respect to P? And the conjecture is yes. And we're saying here we're going to construct the Radon-Nicolem derivative. And then if we can construct a Radon-Nicolem derivative, we're going to get the implication, right? So let's try to construct this random variable. Try to construct a random variable. So we return to the example. So this is this example continued. We want to construct dq/dp such that, for example, q of x less than x, this can be found by integrating. What are we doing here? We're integrating over the set A. So here we're looking at x less than x of the Radon-Nicolem derivative dq/dp, and then you integrate with respect to p. So we want to construct this thing here so that we have that. So we get the idea that probably this Radon-Nicolem derivative, this is a random variable, it's non-negative, it has expectation 1, and it should satisfy this property, probably. So we're going to make a guess that this dq/dp, this is probably some function, we call it z of the random variable x. This is probably some function, z that goes from r, and then it's never negative. So we'll just guess it has this form and find, z. Well, the first thing we can do is we can take this guess and we can plug it into the formula here. So on one hand, we'll have q of x is less than x. This is going to be equal to an integral over x less than x. Then you have this z, the random variable x. You integrate in respect to the measure p. Like, remember, this here is nothing else. This is just longer notation for an indicator for x less than x, z of x. Right, these two things, they mean the same. And so what I can do is I can write this here as, I can use that integral transformation theorem that we talked about last time. we can express, if I know that there's a density for x, I can express these expectations as integrals over the codomain of the random variable x. The random variable x has a codomain r, so I can integrate over r. And then I have to replace the random quantity by a dummy, so this will be a little y less than x. And I integrate the function that I'm hunting. This is my z of, I replace the random variable by a dummy, so that was my little y. And then I have to multiply onto the density. I am under the measure p. And so what happens under the measure p is that I have, under the measure p, I have the normal density. So I'll plug that in there. 1 over root 2 pi e to the minus y squared over 2. And then I'll have a dy. Of course, this indicator here, this is going to give me a bunch of zeros. It's going to give me a bunch of zeros as soon as I get past x. And my y's vary over r, but when I get past x, this thing drops to 0. So I can write this here as an integral from minus infinity to x of this z of y of 1 over root 2 pi e to the minus y squared over 2 dy. So this was the right-hand side. Now we can start working on the left-hand side. Well, the left-hand side is a lot easier to work on because we know exactly what this probability is, right? It is this thing here. So I just copy what I have here on the next slide. So it's equal to 0 when x is less than 0, and it's equal to this integral. It's equal to this integral from 0 to x of e to the minus y and dy. Right, so I'm hunting a function. I'm hunting a function that makes all of this stuff here be the same. So what should we pick for z? What should we use for z? Well, what do I want? Yeah, go ahead.
Square root of 2 pi times, we want to make the negative y squared into negative y.
Well, what should we get? What should we get here when the, what should z here be when the y's are negative?
Zero?
Because we want to get that 0 over here, right?
Yeah.
Yeah, so we want this thing to be 0 when y is less than 0. Okay, so if that's the case, then I can replace, I can now write this, because I have that property, I can now write that up here as an integral from 0 to x of z of y, 1 over root 2 pi e to the minus y squared over 2 dy. So now I can match these two. So what should I choose for my z? I want this to be equal to that.
Square root 2 pi times e to the negative, e to the y squared plus y.
Yeah, I'm just going to break it up like that. So that's my radical derivative. And it's always good to just make a sanity check. If you're doing stuff like this, there are lots of chances of messing this up. And so it's always a good idea to make a sanity check, right? And the sanity check, even though it's not going to rule out all mistakes, it's going to rule out some mistakes. Like the sanity check is to have a look at the first two properties. It's just make sure that we didn't violate 1 and 2, right? So the first thing to check is that this is positive, right? Positive in the sense that it can be greater than or equal to 0. Okay, so this is good. And then what we have here, this is an exponential times some constant. We good. That one works. But what about this one? Right, so we make a little sanity check. And the sanity check we're making is that I want to compute this expectation. I want to compute this expectation. So, right, what is it? The QDP was this function z that I have myself created down here, composed with the random variable x. So that would be z composed with x. Okay, I use the integral transformation theorem just as I did here. I'll write that as an integral over possible values of x. Okay, so I'll call those values for z of y. Now I am on the p, so I need to integrate here with respect to the density that the random variable has under that measure. So we go up and look, what was the distribution of x under the measure p? There was standard normal. Okay, so I need to multiply onto the standard normal density here. This is 1 over root 2 pi e to the minus y squared over 2 dy. And does it work? Well, what is z equal to when y is negative? If you look up at the formula for z, when y is negative, I get a 0 in here. Okay, so that will drop out. I'll only have to worry about integrating from 0 to infinity. And what is z in that case? Well, in that case, z has this form, right? And I multiply onto this stuff here. And you see, most of it cancels out. The only thing I'm left with is this e to the minus y dy. And when I perform this integral, I get 1. So this energy check, it works. I'm not violating the obvious properties. And if you're doing a calculation like this one, compute a radical derivative of sorts, you want to make sure that it has the right features, that it's positive, and that it has expectation 1. So this is how I would answer that question 16.
Professor, where did so you don't like the indicator with the 1 y is less than or equal to x, right? Yeah. When you went to the next step, how did we get rid of that?
But what happens to this integrand here when y is bigger than x?
It's 0.
Yeah. So then just integrate, right? So I only need to integrate up to x.
Oh, okay, I gotcha.
Right. It goes from minus r, right? This is from minus infinity to plus infinity. But I can throw away all those values of y that are above x, because the indicator is going to drop down to 0.
And the statement, the qx is less than x equals the integral zx dp equals the expectation with the indicator. The one right above the thing we were just talking about. Yeah. Right above that one. Right. One more above. Yeah. This line. Is that something we just know from the random, like the form of the random Nikodym theorem from like the third?
These two things are the same. This is tomato.
Oh, okay.
Right, because we write expectations as did we not have Thought I had written that somewhere. Like whether we write this expectation as an E, or we write it as an integral with respect to pt. These two things, this is just notation. This thing here has exactly the same meaning as this thing here. That is why I wrote this equality sign here. There's no difference between the meaning of this symbol and the meaning of this symbol. And these two things are the mean exactly the same. It's just another way of writing the same thing.
Gotcha. Okay.
Then there was a question in the blog. Can you please go over again the expectation? Yeah, of course. Of course. Right, so what did we do? This is the sanity check, right? Because these random derivatives, these random variables that we call random derivatives, you have to have a number of properties. And one of them is that they must integrate to 1. Okay, so the first one, that is just our clever guess up here. This random derivative is nothing but a function of the random variable. Okay, so I just plug it in here. I just plug that thing in here. And so now I have an expectation. I have an expectation under the measure P of a random variable. More precisely, I have an expectation under P of a function of a random variable. And that random variable, I know what the density is under the measure, right? So we talked about how to relate these Lebesgue integrals, this guy, how to relate these Lebesgue integrals to the standard Riemann integrals that you have seen in your probability class. And it says you take the function, okay, so that's my z, and you replace the random quantity by a dummy in the image. By a dummy in the image. So you need to figure out what x takes values. So you go back to wherever you have the description of x takes values in R. Okay, so you take a dummy in R, and that's my y. Okay, so I'm integrating over the image of x, R, and then I multiply onto the density function. The density function I have under P. And then you just, well, when y's are below 0, this z drops out. I only have to integrate over the positive ones. Okay, so what happens with z when I'm positive? Well, I get this formula and it cancels out a bunch of the things that's sitting right next to it, and I end up with this e to the minus y dy. And this is the density function for an exponential, and I integrate to 1. One could ask in this context, why not? Well, this was the second part we had, right? What about the first part? Why can't we do that? What would happen if we try to create the radical derivative? What would happen if we try to create the radical derivative between P and Q instead of between Q and P? So we're saying here that this is impossible, right? So the radical theorem says that you can do that exactly if you have a radical derivative. Okay, so apparently something has to go wrong. But what is it that goes wrong? So sometimes it can be insightful to try to do something that you know is not going to work, and then figure out what is it that makes it fall apart. So let me try to do that. So the other way won't work. The other way, so that is P's radical P's radical derivative with respect to Q does not exist. Right, and we can try it, see what happens. But the way that we're going to do it is we're going to plow ahead exactly as we were doing here. We're just switching the roles of P and Q. Okay, so then what I'll start by doing is I'll start by saying, okay, so let me look at P of x less than x, and what I want to have is I want to be able to write this as an expectation under Q of some derivative, maybe call it C bar of X of an indicator X is less than X, right? We are hunting this function C bar just as you're hunting a function in Z here. You're swapping the roles of P and Q. And now this has to fail. So we should not be able to find such a C bar. Okay, so as before, if I am on the P, I know that this is standard normal. If I am on the P, I know that this is standard normal. So here I would write an integral from minus infinity to x e to the minus y squared over 2 dy. That was my left-hand side now. And now I want to work out what the right-hand side is. And now I'll proceed as before. I would switch up the, I would move from integrating over omega to integrating over the image of x. This is over in R. Okay, so if I am under Q, I only have to worry about what do I have to worry about? I have to worry about the indicator that y is less than x times this z bar of this c bar of y, and then we need density, and the density only exists from 0 to infinity, otherwise it's equal to 0. And on that interval, I get e to the minus y dy. And the question is, can I make this thing happen? Can I find such a C bar such that this is true?
Do you not have the thing going into the negative infinity part?
Yeah, so over here it goes from negative infinity to x, and over here it goes from 0 to infinity. So can I make this work? Well, let's try. What kind of an x could be interesting to pick? Well, Alice had a great suggestion. Right? She said, pick this 0. So I want this thing here to be true for all x. In particular, it should be true for x. Okay, so try x equal to 0. If I plug in x equal to 0 on the left-hand side, I get Alice's 1/2. And I'm claiming that this is equal to what happens over on the right-hand side. Well, if x is equal to 0 here, I get 0. But this is impossible. So we can only go one way works and the other one does not work. And it's simply because that P, we do not have this implication that that just because Q is equal to 0, and then necessarily P is also going to be equal to 0. And indeed here, the right-hand side is 0 and the left-hand side is 1/2. So there is no identical derivative. So there is no derivative. This I'll start calling this Rn, identical derivative. Okay, so let's do another example. I know this here is this can be a bit confusing, but maybe if we did something that's been familiar to us for a while, if we go back to the one-period binomial model and have a look at that one. So let's do another example. I do another example. So this is just a one period binomial model. If I do the one period binomial model, I know, what do I have? I have my omega. This is heads and tails. Right, and I know that p is equal to the probability on the p of heads. And then obviously 1 minus p, this is going to be the probability of tails. And we also know that we have this measure p tilde, which is p tilde of heads, and 1 minus p tilde, this is p tilde of tails. And we could ask now, what's the radical derivative between these two measures? So let us find these random variables. We know this is something that goes from omega, and we know that it takes it does not take negative values. How do we find it? Well, we should have a look at p tilde. And this is my p tilde, right? If I want the radical derivative, what I have to be able to do is to be able to integrate over the set. The set here is very simple. It's a singleton, and then I integrate the radical derivative with respect to p. Right, that's the formula. That's this formula I have right here. I get the measured value of the set. I integrate the radical derivative over the set with respect to the other measure. So this equality sign here, I'm just casting it here in terms of p tilde instead of q. Okay, so I'll work out what the right-hand side is. I'm integrating over a single point. So what I'm going to do is I'm just evaluating the random variable at that point. And then times the probability of the set. This will be my p. So then I have an equation that will determine the radical derivative at that point. This is going to be p tilde divided by p. So I got some of it determined. We also need to determine what it is at tails. So if I do p tilde at tails, I know that this has to come out to be 1 minus little p tilde. And of course, I can use the formula again. I will now be integrating. I'll be integrating over a single point t of the radical derivative with respect to p. So what I get, I integrate over a singleton, I'll just get the random variable evaluated at the point times the probability of the set. This was 1 minus p. This was 1 minus p over here. So I solve. And I get upstairs I have 1 minus p tilde, downstairs I'll have 1 minus p. So that's my radical derivative in the one period binomial model. And it's always a good idea to do a sanity check. It's always a good idea to make sure we're not violating the obvious. So a sanity check, well, we have that the expectation of dp tilde dp, that better be 1. Okay, it's a random variable that can only take 2 values, so it can only take 2 values, so it'll take the value p tilde over p, that'll that's the value it'll take if the coin flip is heads, and the probability of a head coin flip under the measure p is going to be p. And likewise, if I likewise, if the coin flip is tails, the random derivative will be 1 minus p tilde divided by 1 minus p times the probability of tails. Well, that's 1 minus p. I cancel all this stuff out, I get 1. Which is something that has to be the case.
So the random negative derivative, is it actually like a random variable?
Yes. Right. A random variable is called a random negative derivative if these properties hold. It's a random variable.
Gotcha. Why did they notate it as a derivative then? It's just kind of confusing that.
Well, the reason that you do it, like, so I should preference this, like, I'm not the one that designed that this should look like this. So why write it as this ratio? Well, I mean, there are good reasons for this. Okay, so let me try to give you some of them. So now we're done with this example here. If we go back to one of the earlier slides. Where was it? Here. Go back to this slide here. Go back to this slide. So often math notation, it is like, it's supposed to help, right? It's not supposed to make your life more complicated. So where does this notation here help you out? Okay, so let's go back and look at the last one here. So if I have both cases, and I get equivalence, what does that mean for the random derivative? So now, we have page 8, page 9. If so, if we're pretending here that say Q is absolutely continuous with respect to P, and dq dp, so maybe I should say this, then dq dp being strictly positive, then dq dp being strictly positive is equivalent to P being equivalent to Q. And just to give you an idea about how would one go about proving something like that? Well, if you look at this example that we had, like that random negative derivative that came out here, it was definitely equal to 0 on a huge chunk, and you didn't have equivalence. Okay, so there's a little lemma here that says that, okay, so this holds if and only if the random negative derivative, if you know that Q is absolutely continuous with respect to P, so you can talk about this random negative derivative. But this here gives us, this implies the existence of this dq to P, which is bigger than or equal to 0. But you're going to get that it's strictly positive if and only if P is actually equivalent to Q. So in that case, what is dp dq? So if I have equivalence, it means that I have both Q is absolutely continuous with respect to P, and it also means that I have that P is absolutely continuous with respect to Q. So that means that there is another random negative derivative if you have equivalence. Any guesses on what it is?
The inverse?
Yeah. This is equal to 1 over dq dp. And so now you can kind of see why does this notation here make some sense. Right? These two things are the same.
Oh, and it also would be greater than 0 in that case.
Yeah, I mean here, so now this here is under the assumption that you have equivalence. So if P is equivalent to Q, what is the random derivative in terms of the other one? Well, it's going to be equal to exactly the inverse.
Oh, so that's why, that's another reason why if you have 0, you get undefined, right?
Yeah, then it won't work. Then it won't work.
Then it wouldn't work.
Yeah, so now what you're doing is now you're up there trying to prove this equivalence, right? That's what you're at now. That's exactly what happens. Okay, so this was just to give you an idea about why did this notation survive? Well, because it gives you a way to remember that if you have something that is strictly positive, it's exactly just the inverse of the other one. I have one more example in mind, but before I put that up, do we have any more questions or comments? So we have a little bit of time left. Let me do one more example, and then let's call it quits. So the next example, this is quite famous. This is Black-Scholes. Right, so Black-Scholes, this is this continuous time model that is coming sooner than we know. So what we're going to do is we're going to create random derivatives. And in Black-Scholes, the way that is done is the starting point is you take a random variable. So you take x. You take x and you say that the probability that x is less than some constant, this is standard normal. So that's the starting point. Take a Gaussian. Take a Gaussian, and then you're going to create a new measure. And then you're going to create a new measure by specifying. So create a new measure. Let's call it Q by specifying its random derivative. Okay, so the way I'm going to specify it is by saying that Q on a set A, I'm going to define this as an integral over A, and then I need to put the random derivative, and then I'm going to write dp here. Okay. And the thing I'm going to put here is going to be an exponential. It has to be positive, right? So I'm going to put an exponential of x. But keep in mind, I need this random derivative to be such that it integrates to 1. So we need to remember, so this is just a little note here, you need to recall the moment generating function for a Gaussian. So if I look at ETX, does anybody remember what the moment generating function is for the Gaussian? Otherwise, it's not too terrible to work it out. I do the same thing as before. I switch from integrating over omegas to switching over, integrating over the codomain, 1 over root 2 pi e to the minus y squared over 2, and then the function e t y dy. Excuse me. E t y dy. So I have to work out what this integral is. And one way to do that, it's almost always the case when you play with the normal that you have to do something with the square.
Complete the square.
complete the square. Yeah, so it's let's see what we get. An integral over r, 1 over root 2 pi, and then it's probably e to the minus 1/2, and then on y minus a t squared dy, and it won't quite work, but it's pretty close. I have minus 1/2 y squared, that's good. I have inside here, I get minus 2ty plus minus a half, so that's good. So the only problematic term is here I have minus 1/2 t squared. I need this e to the 1/2 t squared out here. And so now I just do substitution. I put y prime equal to y minus t, and I end up with e to the 1/2 t squared. So you see that the expectation, of e to the tx, this is e to the 1/2 t squared. I'm looking at a radical derivative that is e to the x. I want e to the x to have expectation 1. Currently it has expectation exponential of 1/2. So I need to correct this a little bit. And you subtract 1/2 here. So that's my new measure. And then often what we want to know is, so if I specify a measure, this here is strictly positive because it's exponential of something. Right, so this is strictly positive. So because e to the x minus 1/2 is strictly positive, q is equivalent to p. We could also be interested in stuff like what is x's distribution under this measure q. But we know it's Gaussian, standard Gaussian under P, but what's the distribution on the Q? Well, one way we could try is to compute one of these characteristic functions. We could compute the moment varying one, or we could try to compute, okay, so maybe this could be a little homework, try to compute the expectation, not on the P, but on the Q of say e to the t, e to the tx, or better, in my opinion, and compute the characteristic function e to the I tx. But make sure that you are under the right measure, because we're interested in x distribution and not on the P anymore, because we know what it is on the P. We're interested in what it is under this Q measure that we have gotten ourselves created using the radical derivative e to the minus 1/2 plus x. Right, this one here, this is the characteristic function. And this one here, this is the moment generating. And the textbook favors the moment generating function. I personally do not favor this one because you never know when it's finite. It's non-negative, but it could be plus infinity. The characteristic function is better because you always know that the absolute value, this is bounded by 1. And this one here could integrate to plus infinity quite easily. Of course, this one here is complex values because you have this I in here, but I mean, we can deal with complex numbers. I would rather deal with complex numbers and then avoid dealing with plus infinity. So I prefer by far the characteristic function over the moment generating one. That being said, the textbook, he likes this one. That's okay. Yeah, this is the Black-Scholes model in a nutshell. This measure that, as I referred to here in the beginning, this measure that takes a full full-blown chapter going through risk neutral pricing here. These many pages here, like in essence, what you're seeing, this risk neutral measure that has been created here, in essence, what you're seeing is nothing else than creating a new measure using this particular derivative. So we'll talk a lot more about that. It has lots of implications that are not trivial and so on. But I think this is probably a good place to call it quits for tonight. Are there any questions before we say good night?
When we created the new measure Q,
yes,
why did we take the moment generating function and like tack on the opposite of it sort of to the e to the big X?
But you need this thing to have expectation. If I compute the expectation of e to the x minus 1/2, what do you get?
You get the
1.
Right, and that's what you needed.
Why do you get 1 from that?
Okay, so an exponential of a sum is equal to the product of the exponentials, right? So this thing here becomes e to the minus 1/2 times e to the expectation of e to the x. Right? And e to the x has expectation e to the 1/2. So that's 1.
E to the
this one here, you get that from what you have down here, where you put t equal to 1.
Oh, okay, t is 1 in this.
And you go all the way over here, exponential of 1/2.
Oh, okay. I didn't even realize. Okay, yeah, I didn't even realize that the t was 1 there. Okay, I got you.
So that's why you subtract away this minus half. If you didn't do that, you see that this expectation here is it's not going to be 1, right? It's going to be just e to the 1/2. And so that means that when I take q of omega, you get that the mass would be just e to the 1/2, and that's not a probability measure. So that's a no-no. You have to have a Radhanickel derivative that has, well, it has to be non-negative, and then it has to be such that it integrates to 1.
The other thing I have a question about was, like there are a set of conditions for something to be a probability measure.
Yeah.
How do we know that? Well, do we have to verify that this satisfies those conditions at all?
Yes. But it does, right? So let's try to check that Q indeed is a probability measure. So the first one is we want to take Q of omega. What do we get there? Well, that's this expectation we've been talking about. Right, that was 1. So then we also need to check if I take, so let's do a simple case. If I take A1 intersection with AB is empty, then I want to check that Q of A union B, what should it be? Well, I want to have that this is exactly the probability of A plus the Q probability of B. Okay, so let's do that. I'm going to be integrating here over A union B. And then this Radhanickel derivative, dq dp, dp. But here I have a disjoint union. So if you integrate over a disjoint union, this is going to be the same thing as integrating over A, dq dp, plus integrating over B, of dq dp. But this is exactly Q of A plus Q of B.
Okay. Got it. Got it.
And then you have to move. You also have to do this for countably many, right? It's not enough just to do it for 2. You have to be able to do it for countably many. So for countably many, use the monotone convergence theorem. And this here is actually a problem that's going to come in one of your homeworks. So you were spot on. Great question. Yep. More questions or comments? Okay, if not, then I bid you all a good night, and I will see you on Thursday.